So we are in live.
Yes, so once students start asking, we'll start with. Okay.
Yeah, sure.
Hi everyone. Hope you can hear me.
Yes, sir. Now we can. And your screen is also
visible, right? Okay, good. So there are enough participation. I can give just a summary about the course. So are there enough number of participants, or shall we wait for a minute or so?
I think we should wait for a minute because
okay,
students are still joining. There are only 10 participants yet.
Right. So out of these participants, are there any questions? Guys, please feel free to ask questions. Till others join, we can go over that possibly. Anyone has any questions? Whoever has joined.
Is it possible to send a gentle reminder to all the participants, all the students?
Yeah, Yusuf Hasan has asked, can you discuss Catalan numbers and their use case once? Okay, maybe we'll start with that, and then once sufficient number of people are there, we will then get into a general idea about the course, where does it come, etc. So maybe I will start with the Catalan numbers, right? I hope you can see my screen, right? Yeah, okay. Yeah, good. See, Catalan number comes in many places when you try to count. Okay, so the number of binary trees. Okay. Yeah. So, and number of possible parentheses. Suppose you have matrices, let's say A1, A2, AN. You must have seen how many ways can you group these matrices so that you can compute the matrix product efficiently. So this you would have seen in dynamic programming. The question here is, what is the best way to parenthesize? Suppose you have two brackets, then let's say two open bracket and two close brackets. So this is one possible configuration. Another configuration is this. And then what else possible configurations are possible with two brackets? These are the possible two bracket configurations. So when you try to multiply n matrices, okay, what you essentially try to do is you try different parentheses and you can exhaust and see which is the one which gives the least one. But there are efficient ways to do the same matrix multiplication, like using dynamic programming. So this is one case where these Catalan numbers come very naturally. And the other case is number of rooted trees. Like suppose this is an example of number of parentheses. Number of ways in which we can have valid bracketing sequence. Another example is where you have number of binary trees. Suppose you take 3 nodes. How many different trees are possible with 3 nodes? So this is one tree possible. Another is, this is one more tree possible. And this is one more tree possible. Like then, this is one more tree possible. So typically 5 such trees are possible. So given n nodes, how many such binary trees are possible? These are some of the common counting problems which you see in computer science. That's when Catalan number comes. The best way to understand Catalan numbers is in terms of its recursion. So for example, so if I have, let's say, n plus 1 brackets, how many ways can we bracket n plus 1 can be written in this following recursive form, which is pk into pn minus k. So k equal to 0 to n. So this is one way. So whenever you see this kind of recursion, then automatically you are going to say that there is going to be some Catalan number in that counting problem. So for example, in the rooted tree problem, how many binary trees are possible with n plus 1 nodes? So 1 will be the root node. Okay. So now how many left subtree node will be there? There could be k subtree nodes, and in the right subtree you will have n minus k nodes. So how many possible left subtrees are possible? Pk subtrees are possible. In the right side, you get pn minus k subtrees. So the number of n plus 1 node subtrees possible is nothing but pk into pn minus k, k equal to 0 to n. Why is this sum? It is because it's a disjoint union of these possible configurations. So these are the places where Catalan number comes very naturally. So and once you know that, you can solve these recurrence, or even from the course you would have seen, Pn is 1 by n plus 1, 2 and choose n. You can solve this recurrence, and you have a closed form explanation for this Catalan numbers. I hope that clarifies your doubt. If you have still some other question on Catalan numbers, we can still discuss that. How many ways can letters of the word mathematics be arranged so that the vowels come together? Could you explain this problem? So, see, I think I don't understand the question clearly. In how many different ways can letters of the word be arranged so that the vowels come together? See, how many vowels are there, first of all? A, E, A, right? The rest of them are all 1, 2, 3, 4, 5, 6, 7. So totally there are 7 non-vowels, and then 4 vowels, is it? Why is that? Yeah, A, and totally there are 11 letters. Is that correct? 7 consonants. So these 4 vowels can be grouped as a single unique digit, right? So there are going to be 8 symbols which you are going to permute. So what you do is there are 8 factorial ways you can do that. But as you know, within a particular unit also you can do some arrangement. What can you do there? Because there are 2 A's and 1 I and 1 E. So within that, how many possible ways I can arrange within that 4 symbols? So you will have to account for that. So how many ways can you do that? Can you type in your answer? So can they also speak up, Poonam, or it's not?
Yes, sir. I think they can. Kamal, can you please elaborate your question? What is your doubt? I think this question is also answered in the video.
Right. It's very clearly answered. So you need to account for these cases. That's all, Kamal. Is it clear what I'm...
Yes, go on.
Sir, is this the solution that we will obtain, sir, or is it the 8 factorial by 2 factorial into 2 factorial?
See, what I don't remember exactly. We will have to do the computation. What you have to understand is when you don't know, okay, what exactly is a solution to a problem. Like, for example, this, take a simpler case. Take only M-A-T-H, let's, for example, or M-A-E-H, let's say. Using these 4 letters, how many different ways can you arrange? You can write it down. Okay, when you have confusion like this, okay, so you will write all possible cases and where you can keep the vowels. Then you will understand where exactly you are missing, because you will have to do the counting precisely. See, once you fix a symbol, then you will be able to permute that symbol. That will give rise to new what do you call, permutations, basically, right? So when you keep it as one unit, that's what happens. Is that clear?
Yes, sir. Thank you, sir.
Yeah.
Regarding
Okay.
the last question, it will be 8 factorial because the 7 are the consonant and 1 is the bunch of vowels we are considering. So there will be 8 consonants.
So totally 8 factorial
Okay.
divided by what? 2 factorial
2
into 1
factorial
factorial.
into 2 factorial.
There are two factorials or 1 2 factorial?
There are two
Only-
2 factorials, I think. There are 2 repetitions.
No, okay, that you will have to check correctly.
Yeah,
I think
and
2 A's are there and
Nice,
1
I
A
got
and
it.
I is there. Yeah. Okay. Good.
2 M, 2 T, and 2 A are there.
Okay. There are some repetitions. So please ensure. Yeah, good. I get it. Okay.
Yeah, yes, sir. Got it, sir. Thank you, sir.
Okay. So how can we expand the Catalan number expression as Pn plus 1 as k choose 0 into? I didn't exactly follow how did the last form come from. Okay. See, let's take a particular example. Okay. So the question is, how many binary tree configurations are possible with n plus 1 nodes? Let's try to answer this question. Okay. So when I have a binary tree with n plus 1 nodes, one of them should be a root, right? That I'm keeping it here. So remaining now I have n more nodes, which I will have to distribute in the left subtree and the right subtree. Now, how many left subtrees are possible if there are k nodes to the left subtree and n minus k nodes to the right subtree? Can you tell me? So how many left subtrees are possible with k nodes to the left subtree? Yeah, you can speak up, Yusuf. That will be great.
Sir, k choose 0 plus k choose 1, so on.
No.
till k.
See, you think you understand this is a recursion. How many left subtree possible is pk? See, what is Pn plus 1? It is the total number of binary tree configuration possible with n plus 1 nodes. That is the definition of Pn plus 1. So pk is the total number of binary tree configuration possible with k nodes. Is that clear? By
Okay,
definition
sir,
of,
yeah.
yeah. So pk possible tree configurations are there by and Pn minus k right subtrees are possible. Okay. So total number of trees possible is by multiplication rule pk into Pn minus k. So those many choices are possible in the left subtree and these many choices are possible in the right subtree. So how many possible altogether? Pk into Pn minus k. But then k can vary from 0 to n. I will have 0 nodes in the left till n nodes in the left subtree. So that's why it is summation pk Pn minus k. Is that clear?
Yes, sir.
So even in the bracketing case also, you first understand where does the first bracket end. So assume it ends after including k such left brackets. So you will have pk left bracketing possible, and similarly from the rest of the n minus k, it will be Pn minus k. So now you sum over all possible k from 0 to n. That is how you get n plus 1 left and right bracketings. Is that okay?
Okay, sir, you have initially defined a recursive function only.
No.
This
I did. Which one?
This Pn itself is a recursive function, right? That's what
No.
we are saying.
No, see, if you write see, what is the meaning? In order to find how many different binary tree configurations are possible, you will look at one, you are going to group things in the following manner. So anyway, there is going to be one root, correct? And there will be some number of nodes in the left subtree and there will be some number of nodes in the right subtree, correct? So I'm going to assume that there will be k number of nodes in the left subtree and n minus k number of nodes in the right subtree. Okay. Now, if I have k nodes in the left subtree, by the definition, how many binary tree configuration are possible? That is nothing but pk. Okay, by definition. Similarly, right subtree Pn minus k, different binary tree configurations are possible. Okay, and therefore, pk into Pn minus k is the total number of tree configuration that are possible with k left subtree nodes and n minus k right subtree nodes. But then we know that in left subtree, there can be 0 node, 1 node, 2 node, 3 node, until n nodes. Okay, so once you choose the left subtree, how many nodes? Automatically, the right subtree, the number of nodes get decided, and so many trees will get, so many trees are possible in the right subtree. So using this, you will be able to compute it. I think it requires little more thinking. Okay, the definition is you should understand Pn plus 1 is the total number of n+1 binary tree configurations with n+1 nodes. Then by that definition, K represents the number of K node binary tree configuration. So if you understand these things clearly, then it will be easy to write the recursion. Similarly, Pn minus K. Okay, so Pk into Pn minus K is the number of binary tree configuration with K nodes in the left subtree and n minus K nodes in the right subtree. So then finally, so this is because of the product rule, if you understand it. And this sum is coming over is sum rule. Okay. Yeah. Yeah, this is a topic of Catalan number. Correct. I hope this clarifies some of your question. Think about it further. Okay. And go back and see where the recursion comes from. Okay. You can take a particular example and try to see what we are doing in that example. That makes it very clear. Okay. You should. Yeah. Are there any other questions? Yeah.
No, sir, I understood this part. Like, can you explain how the final expression then came from here? You wrote PK something.
No. Pn+1, number of possible binary tree is nothing but this. By the definition, right?
Yes, sir.
Maybe, yeah. I'm not sure whether we covered this part in the course, this particular recursion. But this, you can see that why this recursion should be true. See, in the course gives a proof of the number of possible Catalan numbers using proof by bijection. Okay, so basically you count number of total number possible and how many violations are happening, you subtract them, you get the total number. So that is a very interesting proof. Certainly that's a very good proof also. But along with that, if you understand this recursion in the case of Catalan numbers, it will help you to do see many problems easily, which involves Catalan numbers. There are so many problems. So number of random walks. Yeah. So it's not exactly in the course. I agree, Alok. I understand. Yeah. So I'm trying to tell some additional part. Yes. But
so what Sir did in the course, sir, he actually showed that bijection thing and he generalized it after the example. He said that this happens on these many 5 things. So he said it can happen on n as well. I think that's what he did.
Right. But what I'm saying is that is certainly true, but that will come only after some experience. So you need to do a lot of problems in order to see if a given problem will be having this Catalan number sequence or not. In addition to that, if you understand there is a recursion underlying that, okay, which is this PKPN minus K sum, okay, the number of random walks without crossing 0 and things like that, then you will understand this recursion is going to come very easily. And then once you see that, then you will automatically understand that it is going to be Catalan numbers. Another way to see this whole thing is you write for small examples, 2, 3, 4, and see how many, like what is the answer for the number of possible configuration you want to count for. And then based on that, you can generalize and see that it will be a Catalan number. Another interesting problem is number of ways you can triangulate a hexagon. Let's say you have a hexagon. How many ways you will be able to have triangulations of this hexagon. So for example, this is one triangulation, one direct simple triangulation. Another way is, let's say you put the connection like this, then you connect this. This is a different triangulation, right? Or maybe this is the same one possibly. But let me see. Yeah, this looks identical. So for example, let's take this we join this and then we triangulate the following way. So I don't want, there are so many problems which involves Catalan numbers. So here you will not see exactly that. So the number of possible ways to triangulate a hexagon may not be P6. You will have to correspondingly see whether it is P6 or P3. Exactly. So P 14 ways you are saying, right? So 14 is what Catalan number? Is it P2, P3, P4, or C1, C2? I am saying, okay, I used a different notation. Maybe that's why maybe it is slightly confusing. Yeah, I should have used C. Maybe that was one trouble. Yeah. So is it C1, C2, C3? You can verify. For triangle, it is just one. Okay, so for a triangle, there's just one way. And suppose you have a four-sided figure, then you have two ways to triangulate it. This one and this one. So these are two ways. So you will be able to exactly do this calculation for any general n-gon. Okay, that also involves the number of ways to triangulate an n-gon has a Catalan number sequence, but not exactly Pn or Cn. Yes, C4. Yeah. Thank you.
So sir, here can we write the recursion as sigma k equal to 0 till 6 Pn and Pn minus k from 0 to 6?
Not 0 to 6. No. See, you have to understand. So in this case, you have to understand it is not Pn plus 1 you are talking about. Look at this. See, when I have a n-gon, this particular corner, I can connect with how many, what are all the possible corners I can connect it with, you tell me. This is 0, this is 1, this is 2, let's say 3, 4, 5. Now, 0 and 1, 1 and 5, already it is connected. Okay. So you can connect this to either 2, 3, or 4. Only there are 3 possibilities. The first, take 0, you can connect it to one of these things, right? And then what you do is, now these 3 possibilities are k equal to 0 to 3 or 0, 1, 2. There are 3 possibilities. And in each case, you are going to get some number of Catalan numbers to the left of that and some number of Catalan numbers to the right of it. For example, suppose I connect this, then this will correspond to C2 to the left of it. And then similarly to the C2 or C1, because yeah, you have to exactly identify this will be C1. Similarly, here it is going to be C2. So this is C1 into C2, we are saying. Okay. So you need to compute it in this manner. Is this clear what I'm saying? So you are starting with 0 and you are connecting with one of the n minus 2 vertices. So I need to sum from k equal to 0 to n minus 2 and ck cn minus k. That's how you get the cn. Okay.
Yes, sir. Understood.
Right. So this recursion, you will be able to see it. Yeah. But directly also, when you try to enumerate it, you will be understanding that this will be the Catalan numbers. Hope that is clear. Okay. Any other question? Can you give basic about where to use permutations and where to use combination? So, see, I think you should understand based on the problem, n minus 2 minus k. Yeah. Thank you. Correct. Yeah, you are right, Alok. Yeah, right. So maybe I will correct it. See, once you understand the recursive idea, you should be able to directly write it correctly. Okay, thank you for correcting. Yeah, because k is varying from 0 to n minus 2. That's what we are doing. All right. So, yeah, fine. So for the permutation and combination, you should see what is meant by permutation. Then it is like you have n letters. You are trying to find out how many ways you can arrange the letters, right? That's what permutation is about. Now, in combination, you are choosing some k objects out of n objects. So automatically it is clear where each problem is coming from, right? So you have n people, you want to select a team of k people. How many ways can you do it? That will turn out to be your combination, number of ways of choosing k people from n people. Suppose you want to arrange k people, like let's say for a photograph, then how many ways can you arrange? Then maybe out of n people, the first there are k slots. So in the first slot, you can get any of the n people, and in the next slot, you will get n minus 1 people, and so on and so forth. That's where you get the permutation, right? NPK, right? That's NPK and NQSK. Is that okay? Kamal, I assume you understand what I mean. Yeah. Is there any other question? Okay. Fine. There were some questions which were asked in the the link. Maybe I will start with one of those questions, which was in the combination. Let me just. The question is, so in order to find how many. So the question is as follows. There are 10 elements. So suppose a set consists of 1 to 10. 1, 2, 3, dot, dot, dot till 10. Now, how many subsets of S includes the element 2 and 5. So basically, you have to be careful when you're trying to count. Okay, how many sets of S include the element 2, 5? So direct way to see it is, so now 2 5s are taken care. Now there are going to be 8 elements which are going to remain right now. Okay, now what do you do then? You take those 8 elements, how many ever possible subsets you create with them, you create it and include the 2 5 in that. So how many possible subsets you can create using 8 elements? That is nothing but 2 power 8. In each of these subsets, you are going to just add 2 5, include the 2 5 in that, and it will create a set which contains 2 5. You can argue that this will exhaust all possible sets which has 2 5. So that is going to be 2 power 8 subsets. This is the correct answer. But alternate solution, which is a wrong answer, like with wrong argument, is what he asked. What is the mistake in that? Let me just go over that. So because where you can go wrong, you will understand. So the approach what the person has mentioned was, there are totally 2 power 10 possible ways in which you can arrange these, choose these sets, 2 power 10. Now, and then this is the total number of subsets. And then I'm going to subtract number of subset which do not include 2 and 5. So how many subset do not include 2, 5? Anyone can say it in the chat. It will help. Let me see. Okay. How many sets do not include 2, 5? Here. Anyone can just put it in the chat. The way he argues is, this is 2 power 10. Number of subset which do not include 2, 5 is, there are 2 elements, you will ignore it. So there will be 8 elements left now. So this answer is 2 power 10 minus 2 power 8. This is what is his argument. But the problem is the following. The number of sets which do not include 2, 5 may have only 2, only 5 in it, right? So basically the way you have not, what you have not removed is, this is not equal to your answer. This is not equal to the real answer. So how many subsets? So let's call this, how many subsets of S includes the element 2, 5. Let's call it X. This is not equal to X, is what I'm saying. This 2 power 10 minus 2 power 8 will also have subsets which will just have 2, which may just have 5. So you will have to remove those things from this. So you will have to, so from this 2 power 10 minus 2 power 8, let's call it Y. You may want to see how many subsets are only having 2, how many subsets are only having 5. Based on that, you will be able to come up with an answer for X. So for that, what you do is, Y is nothing but how many subsets contain only 2, then that will be 2 power 9. How many subsets contain only 5? That will be like include 2 and include 5. That will be 2 power 9. This may include, these subsets may include both 2 and 5 also. So 2 power 9 plus 2 power 9 minus how many subsets include both 2 and 5, right? This will be X. Okay, so you can find X as follows, like Y is 2 power 10 minus 2 power 8. This is again 2.
Sir, I'm not able to understand.
Okay, I'll tell you. see what he has told, the wrong argument. What is the problem with the wrong argument is what I'm trying to tell you. So I hope you understood what is the wrong argument. So 2 power 10 total number of subsets are there. And I'm going to subtract the number of subsets which do not include 2, 5. So that should be my answer. That is the claim. Okay. But I'm saying that is not correct for the following reason. 2 power 10 minus 2 power 8 includes all those subsets which may contain only 2. We have not removed those subsets. Means in Y, you have subsets which contain only 2, only 5, and all those things. So somehow you will have to remove those subsets which contain only 2, only 5. Then you will be able to extract your final answer is what I'm saying. Is that clear to you?
Sir, in the original question, weren't we asked to find the number of subsets which do not include 2 and 5?
No.
Or do they include?
See, the question is how many subsets of S includes the element 2, 5? A direct answer would be 2 power 8 subsets, because you take any remaining 8 elements, you whatever possible subsets, you include 2, 5 in it, and that will be the number of possible subsets which include both 2 and 5. Is that okay? But a wrong argument is what someone has given, and he's saying why this is like what is wrong with my argument. So the argument he has given is I will take the total number of sets and I will subtract the number of sets which do not include 2, 5. So how many subsets do not include 2, 5? That is 2 power 8. So 2 power 10 minus 2 power 8 is what he claims to be the answer. But that is incorrect for the following reason. Because in this 2 power 10 minus 2 power 8, you have subsets which include only 2, and it may not contain 5. For example, one singleton 2 is part of this Y, which we should not really count. Any other subset which contains only 2 but not 5 is part of Y. So we should not include that. So in order to exactly count how many subsets which can include both 2 and 5, what we do is Y we are writing as how many subsets which include 2, and it may include 5 or not, I don't care. So using this is the following thing I'm using. N of A union B equal to N of A plus N of B minus N of A intersection B. A and B are number of sets containing either 2 or 5. Okay, that's what A union B is. So A number of subsets containing only 2 will be A. Number of subsets including 5 will be B. So how many subsets are there which will include just 2? That will be 2 power 9, right? Because the original argument, I'm trying to recover the same answer, but it requires something from our original argument. So 2 power 9 possible subsets are there. Again, it includes only 5 will be 2 power 9. The X is which includes both 2 and 5. So now I can write this Y is equal to 2 power 9 plus 2 power 9 minus X. So if you look at it, then you can directly see that X is 2 power 8. The argument which he did, what was incorrect? The incorrect thing was when you are trying to subtract out, do not include 2, 5, you are including the possibility of having only 2 or only 5. That's why you are not getting the correct answer. Okay, so basically it is becoming Y is actually 2 power 8 into 3. Like if you take 2 power 8 common, it is 2 square 4 minus. So you have 2 times 2 power 8 additionally you have included. That is because you have included sets which contain only 2 and only 5. That's what I'm trying to claim. Is that okay? Or still not clear? For the guy who has asked that question, you should be able to at least appreciate. Yeah. Any other questions?
So when we were removing 2 to the power 8, initially it was we were saying that 2 to the power 5 is never there, and for the other element 2 and 5 are never there, and we were saying that every other element has the option of being included or removed. That's why how we got 2 to the power 8, right?
So why did this 2 power 8 come? That's your question, right?
Initially when we took that.
Initially, first case argument you are saying?
No, in that only, in the wrong one, the 2 power 8. Like,
how did we do? That is the same thing. See, 2 elements should not be included. Remove that element, right? 2 and 5, you remove it. Now, how many elements are there? 8 elements are there. How many subsets are possible which do not include neither 2 nor 5? That is 2 power 8, right? Because See, what we did in our initial argument also is the same thing. How many subsets are possible without including 2, 1, 5 is what is 2 power 8. Now we are trying to subtract it from 2 power 10 here. But there we just, for every set, we just took it and included 2 and 5 and we created a new set which contains 2 and 5. That is a bijection. Basically, we established. But here we are trying to remove those subsets which do not include 2 or 5. Okay, so there will be 2 power 8 such subsets. So we are removing it from 2 power 10. That is what he claimed to be the answer, which is incorrect is what I'm saying. Is that okay? Okay, good. See, I think whatever argument I am saying, maybe you should think one more time, like after you go back. Okay. Due to lack of time, we are going to do it a little bit faster. But if there are no questions, I can go in more detail as well. Yeah, but you have all these things anyway recorded, so you can think on your own as well. Okay, like everybody has their own rate at which they can assimilate information. Like, so you can think about it and then you can understand, I assume. Okay. So any other question? So these are some of the questions which I saw was asked specifically. Any other specific question right now? Quoting total number from 00 to 55. Okay. Why is that? Look, what is the problem? It's quite total number of ways. See, you just, shall we do it for a smaller number? So otherwise it will become difficult to draw the grid. So 00 to 22, is that okay with you? Hello.
Yes, sir.
Yeah. See, this is 00. And then 10, 20. Similarly, so basically I'm trying to draw this grid. This is 10, 20. This is 11, and then 12, 21, 22. Right? See, if you notice this 00 to 22, how many? Whenever I have to make how many ways are there? You can assume that whenever you move horizontally, you're going to move right. And when you're going vertically, you're going to go up. Let's say this is one path. Right, up, right, up. RU. This is one particular path. So if you notice this, in any path from 00 to 22, how many rights are going to be there? You can type in the answer. How many rights should be there? Okay, 2. And how many up should be there? Yes, very good. So the question boils down to how many ways we can use or we can arrange two R's and 2 U's. So that is nothing but how many ways? Can you tell me? How many ways are there? 4 factorial by 2 factorial.
2 factorial to 2 factorial. Yes.
So this is one way to understand, or other way to see it is, so there are n positions. First, I will fill how many rights. So there are totally 4 choices and there are 2 spots. I will choose 2 spots, then the remaining spot automatically gets filled. So it is also 4 choose 2. Like this, you can directly argue, right? So in general, 00 to nn. Okay, so you need to have n rights and n ups. So totally, you are going to have 2n factorial divided by n factorial. These many paths are possible from 00 to nn. Now, in the direct way is, there are 2n spots in which first you choose n spots where you want to place your right, let's say. Then up automatically gets fixed. So that is the same thing as 2n choose n. Both are equivalent. Is that clear? Hello?
Yes, sir.
Okay, good. Any other question? Let me see if there are any question from the list. Okay. So this was the only question which was very precise, at least. So I discussed that. Right. So maybe I'll give a general, possibly a general understanding about what this code structure, how it gets used. Many people have asked that particular thing, right? So maybe we'll do that. So where does this course, how does it help typically, right? So I want to give a quick answer. So what you have to understand is, see, computer science is about study of systems and how things like how different systems interact, computers basically interact, and how do we write program to make a system do what we want, and can we develop some applications using these computers. So typically computer science can be broadly, this is just one way categorization. It is not like this is the ultimate categorization. You can divide the computer science aspects into three stuff. One is the systems, where you learn about computer architecture, operating systems, and maybe databases and other things. And then you have theory, where you learn algorithms, data structures, algorithms, and then automata theory and programming language verification, like automatic programming language verification, such things, NP completeness, all these things comes in this. And then intelligent systems, where you study AI, you study machine learning, you study reinforcement learning, computer vision, various AI related ideas here. So this discrete structures or discrete mathematics becomes very useful in all these places. Becomes very useful under all these three categorization, like under all the three categories. So for example, in theory, it becomes very straightforward. There are a lot of counting problems you are going to see in algorithms, right? So these algorithms, we will discuss 8 questions. We'll see. Yeah. So, so the discrete structure becomes useful in all these three categories. So, for example, in systems, what do? It is about understanding how does a system work? What are the components of a system? Okay. So, how does a programming language work and interact with the system, etc. also comes there, right? So, in understanding programming language, this is very important. Logic. So, you need to have the right kind of logic in order to come up with a proper syntax for compilers and things like that. And in theory, it's very easy to see. Suppose you are designing an algorithm and making a program run. Okay, so we need to understand how many steps it is going to take for the program and how much time it will take. Roughly, you should be able to compute beforehand itself, right? What is the running time of this? Is it order of n square, order of n cube, and things like that, right? So that's where the theory comes in. So in theory also, you have computational model and you have computing theory or the logic. You have what do you call complexity theory, right? And in complexity theory, those problems which cannot be solved in polynomial time. So you study how hard are these problems. So we study NP complete, NP, all these things. So there also these notions of counting comes. See, counting is a very basic science. Okay, so most of the discrete structure, if you try to understand, is about counting, logic, and how do we do this counting by using the idea of sets, right? So that is the essence of this discrete structure course. So intelligent system uses not only discrete math, it uses also continuous math. So in continuous math, but the foundation is discrete math. If you understand discrete math only, you'll be able to do calculus on that. You will be able to do other linear algebra and other higher mathematics. So this forms a basis for all the computer science course. Okay, so that's what discrete structure is about. And typically in discrete structure, you study the following, which is, see, all the contents are not covered in the course, but the very essential things are being covered in the course, right? So the first thing is permutation and combination. Basically, it's about counting, right? So how do we count things? But if you do naively counting things, you may get into some kind of paradoxes, etc. So you need to understand in terms of set theory. So first you understand how can describe this counting through sets, and then logic. So this comes together, set theory, logic. Okay, and you study about functions, relations, etc. Generalization of function, you get relation. So with these things equipped, you will be able to do counting better. So there are advanced counting techniques. That's what you will study. Counting techniques and proof techniques. Like pigeonhole principle, you get to prove mathematical induction, generating function. All these things can be thought of as both counting as well as proof techniques. Okay, then you study some graph theory as well, and basic group theory is what is covered in the course. It's roughly the schema of the course, right? Okay. Yeah. So this is what you study in a fundamental discrete structure course. So you can, if you have interest, you can pick up one particular thing and then you can study advanced topic in that as well. So group theory is covered very basic in the course. So if somebody is interested, they can go back and then see what are the important things where group theory gets applied to cryptography or coding theory and things like that. Okay. All right. So maybe there are some questions. So could you please talk about how the course is oriented for GATE? Oh yeah. Okay. See, this is, as I told you, this is a fundamental subject. And if you don't understand this, it becomes many times difficult to understand other topics. So for example, in systems, it's getting used. In terms of intelligent system, it is getting used, right? In algorithms, it is getting used. So everywhere, it is going to get used. See, by doing this course, you are going to learn to principally do the counting, and you are getting your logic straightforward. So if you will not do wrong arguments in the logic and things like that. As you know, in GATE also, you have both, you have all of these topics basically, which is going to be part of it, but it won't be coming like in a very simple, straightforward manner. You're going to use multiple things and that will come in a single question, right? That's how it comes. So this becomes very fundamental. So once you understand this, trying to understand other courses becomes easy. So that's why this is the most fundamental course, and you typically study it during once you enter the computer science as maybe second year, then you will be studying this particular course in the third semester. All right. So,
Sir, I have a doubt. Sir, in the above example, you have shown 0,0 to 2,2 how many ways?
right.
So, sir, I have doubt that what if we don't pass the diagonal, sir? Because I have problem in that too. Also.
See, that. So okay. So your question is,
sir, sir, logic was too hectic for me. I do not understand anything.
No. It is. See, I am not. It is not. It is okay. It is difficult. You cannot. You will have to see other references also. See, it is a bit deep. That the proof is little deep. The proof is called mirror technique to prove that the number of Catalan numbers is 1 by 2n plus 1 2n choose n. So that's why I gave some alternate interpretation when we started, that there is a recursion. So here, how can you understand that recursion? Okay, so see, suppose you agree to me that a Catalan number Cn plus 1 can be written as Ck Cn minus k equal to 0 to n. So this is the recursion that Catalan numbers satisfy. Okay, so in this case, you want to count how many paths do not cross a diagonal. Okay, so does this recursion come in this problem? How many ways in which you can traverse from 0, 0? How many paths from 0, 0 to nn that do not cross the diagonal? So what we are saying is, suppose you started with some path, you have to reach the diagonal. So the first time I'm meeting, okay, the kth configuration that I'm going to kth position, k comma k. So you start from 0, 0, and you will have to do some rights and ups and you're going to reach the k comma k configuration at some point, right? So that k can vary. Okay, it can vary from 0 to n and things like that. So how many ways are there? Okay, in how many ways you first time you reach k comma k without crossing the diagonal, and then onwards again you reach the final destination point from k comma k to n comma n. So you can think of this, the number of ways as ck. The number of ways to reach from k comma k to nn is cn minus k. Okay, ck is the number of paths of starting from 0 and reaching k comma k without crossing diagonal. So first time you come back and join the diagonal is at k comma k. Now, similarly, what you do is you think that you're starting from k comma k and then again reaching n comma n rest. So number of ways in which you start from k comma k and reach to n comma n. So in order to count this, so you can do C of n plus 1 is equal to C. So basically this recursion holds there also, you can prove it. Okay. So that is the way to think the number of possible paths from 0, 0 to n comma n without crossing the diagonals. Okay, you see whether that recursion is going to come. So the proof, whatever sir has given, is little bit, it is not straightforward. So it requires a lot of thinking. So I can possibly go over that as well, but let's see if there are other questions first, and then we'll get to that. Yeah. Okay, there are only a couple of questions, so we will see. So is this argument clear, whatever I'm saying right now? Does
Yes.
that recursion ck c n minus k come there or not, you see? So what is ck means? First time I start from 0, 0 and I have to reach some kk without crossing the diagonal. That will be ck, and from kk to n minus k, like that. How many possible paths are there? Now, that is one way to look at it. I'm just trying to give you that intuition that this recursion is going to be part of this. So in order to go to the proof given in that lecture video, what he's trying to say is, in order to count number of possible paths which do not cross the diagonal, let's take the total possible paths. That is nothing but 2 and choose n, right? And then
Yes.
how many paths will violate? Basically means it crosses the diagonal at least once. So what I have to really count is how many paths are there that cross the diagonal at least once. Okay, so that is one. So what we are doing is, in order to count this, how many paths that cross the diagonal at least once, what are we going to do now? We are going to see a configuration which has violated. Let's take an example. Suppose n is equal to 3, which means I want to do 0, 0 to 3, 3. So that means I need 3 rights and 3 ups in order to reach that. Okay. Now, suppose you take this path, right up, right up, right up. Tell me whether does it cross the diagonal or not.
I think no, sir.
See, you can see it and then clearly see it doesn't cross the diagonal. You can draw it also and see. The reason
Yes,
why
sir.
it doesn't cross the diagonal is number of rights is
Right,
always
right.
going to be more than number of ups at any point in time. Okay, or all these are valid bracketings. Anyway, you can see it. Okay, so these are the things which do not violate. Basically, we want to really count these kind of things. But suppose you have something which violates. Let's try to understand example of violation. So let's take this particular example. RR, UU, RU. So this maybe, okay, here also I think it doesn't violate. So let me just put the correct one. Right, up. Right. Does it violate?
Yes, sir.
Where does it violate?
Sir, at third U, sir.
Right.
Right, up.
Right. Now, what he's saying is, in order to count how many such violations are there, what he's saying is the following. You consider where the violation comes first time. So that is this up. So this is the place where the violation comes. So there will be 3 U's and 2 R's. Right? This is where the violation comes. So basically, okay, sorry, this one, two U's and two R's. That is where the violation comes, right? Correct. Now
Yes, sir.
I will swap that U to R basically. So how many U's are going to be there then here in this case? So initially you had 2 and choose N. That is what it is in general. Now I will swap this U's to R. So I have swapped this U to R. So how many U's will be there? Okay, I think I made a small mistake. Wait, let me see. So we have to take this part. So basically, this is where the violation happens. So you will have to mirror the rest. So this U will become R and this will become UU. Okay. So this string gets transformed into this string. So in this string, how many U's are there and how many R's are there?
So 2R and 4U.
Correct. So you take any string which is going to have a violation. Okay, you take anything, you go and think about this. Okay, you take a string which has a violation, and now wherever the first violation happens, from the next point onwards, you need to swap it. Okay, when you do that, you're always going to get 4 U's and 2 R's. Always. Any string which is violated, if you swap it like the way I suggested, you will get 4 U's and 2 R's. You take another string, just as an example. Okay, take another violation string. Give me another violation string. Let's start with U. Let's start with U. Okay, U R R U U R. Okay, so this is violating because it starts with U. So you have to take this particular portion where the violation has happened and swap R's to U's. So basically what happens, you will become 2 U's, 2 R's and 1 U. So basically, again, you look at it and you have a string with 4 U's and 2 R's, right? So you take any string which is violating, okay, and after the violation, you take the rest of the string and then you swap to the one from R's to U. Then you are going to get a string with 4 U's and 2 R's. Okay, so this is clear. You can verify it. Okay, now, so what essentially he's saying is the total number of string is for 3, 3 is 3 R's and 3 U's. That is going to be 6 choose 3 minus these many strings which are going to be the violation strings, which is 6. Okay, so here how many strings are possible with 4 U's and 2 R's?
62.
6 factorial divided by 2 factorial into 4 factorial, or 6. Yeah, okay, 6 choose 2, correct. So that is exactly the thing. So in general, you have 2 and choose N, okay, and wherever you are going to violate, okay, so how many things are going to be there then? So some point violation is going to happen, okay, and when the violation is going to happen, the number of U's is going to be more than number of R's, okay. So for N equal to 3, it becomes 2 3s are 6, choose 3, and here you became 2. 1 second, I think, is this correct? 4 5 6. Yeah. So what does it give us? 2 and choose N into if what is going to be the number of ways in which how many U's will be there here? 2n plus 1 U's, right? And I'm assuming there will be n plus 1 U's or ups. I hope this is correct. Let's try to do the calculation. Okay, so this boils down to this particular thing. Minus, is this correct? If I have done any calculation mistake, please let me know. This is in general. So you can take 2n factorial out and then n factorial out. So then this becomes 1 minus 2n plus 1. So I pulled 1, n plus 1 will remain. So here, is there a mistake here? Maybe I cannot
I
pick.
think it should be 2n only instead of n plus 1. So
Sorry.
4R and 2 is 6 only, na?
Correct. Sorry, thank you. Right. So then, right. 2n factorial, good. So now you have n plus 1. I pulled this out. and then there is a n minus 1. So I put a n up in order to compensate, right? Is that correct?
Yes.
And yeah, so then you get 1 by n plus 1 into 2n chess n. Thank you. Yeah, so as you said correctly, this is going to be 2n. So what we have done here is the following. So whenever a violation happens, from that point onwards, whatever is the remaining string, you are going to swap it, mirror image, you are going to take it. Okay. So when you do that, you are going to see that this is going to be the number of strings with n plus 1 use and n minus 1 writes with the total number 2n. Okay. So that's why we got 2n choose n plus 1. I hope this gives you some clarity. Maybe you will think about it possibly, and then you will understand. If you still have some questions, let me know. Is that clear?
Yes.
Okay, thank you. Think about it. It's not very obvious. It requires some deep thinking because it is called a mirror, proof by mirroring. Okay. There are some links you can read about it and you will get much better idea. How did this originate from? Because we don't have sufficient time, I won't be able to discuss that part. Okay.
Sir?
Yeah.
So in the video, we had started with a right first and then went up. And we were saying that more ups will cross the diagonal, right?
Right.
What if we had done the opposite? If we started with up and then went right?
Even then the
Would
same
it
answer.
matter?
No. What is your question? Can you repeat your question? So
I'm saying that are these two possibilities separate, going first right and then up, and either first up and then right? Do we need to count them separately, or is it accounted for in when we only think about it first right and then up? Are they accounted?
No. You please understand what is the main question. That is when you do a mistake. See, we are not saying these two are complements. Violation means something may cross the diagonal up and then can come back to the diagonal. See, the question is how many ways can you reach from 0 to nn without crossing the diagonal, right? That is the question. Now, if you also ask the question, how many ways to reach from 0 to nn, and you cross the diagonal, but you never come back and cross the diagonal. So there are two ways. So these two are totally different questions. You understand, right? But the solutions to both will be the same thing. What I'm saying is, in the number of ways in which you don't cross the diagonal. Okay, let me give you an example. So I don't know whether I understood your question very correctly. So how many ways to reach?
Sir, I was just asking that whether it matters if you go up first or right first then up.
No, it doesn't. But then the question has to be rephrased, is what I'm saying. Someone else is saying something.
I was just rephrasing his question.
See, if you go up first, then it means you are violating immediately, right? You're crossing the diagonal. Na? You get it? See, suppose you went up first, that means you are doing immediate violation. But instead, if you are going right, okay, that means you are not violating yet.
Sir, if we go up first, then that doesn't directly violate the question, right?
No. It does violate.
If it takes first up and then two rights, then that will cross the diagonal.
No. Already you have crossed the diagonal. See, here also you have crossed the diagonal. You should not move up first. See, you have to understand the number of ups at any point in time should not be greater than number of rights. That is what is a violation.
Sir, but if we have gone the first up, then we are in the upper half, right? So we have still not crossed the diagonal, right? The right.
See, this is also diagonal, right? No. You have misunderstood. So take only just 0, 0, 1, 1. Okay. Now we will be able to exhaust all possible paths. Okay. So now you say right up. Okay. So this is one path. The other path is how much? What is the other path? This is up and then right. Right? These are the two paths. Are there any other paths I have missed?
No, sir.
No, sir.
Okay. Now look at this. Now, if you say, in this case, the number of ways in number of paths is 1 right, 1 up is there. So 2 choose 1, it is 2. So the answer is coming correctly. Correct? In the case of total number of paths. Now, if you use the Catalan number calculation and do whatever you are saying, okay, then what should be the answer here? What is the value?
are getting 1, I guess.
You should get 1. But then if you are saying 1, which one is that?
So like
See,
in that,
certainly this is not, this is good. This is a good part. This is the wrong part.
Actually, sir,
why
the question here is there shouldn't be consecutive 2 ups or 2 rights.
No,
So
no.
that would violate, right?
No,
Instead
it's
of
not. See, the question you people have misunderstood. I think you guys have to go back and see the videos. The question says, right, it is supposed to be at any point in time. So basically, when you have 0, 0 to n, you need n rights and n ups. That everybody agrees. In order
so
to
just one thing,
yeah.
can I clarify the question? So is the question asking us that how many ways can we, when we violate a path, it means we are from the lower triangle, we have moved to the upper triangle. That's called a violation. And if we directly go to the upper triangle, that is also a violation. That's why the first step is also a violation. Is that what we are saying, sir? Like
No.
if we have gone across 0, 0 to 1, 1 any time in the upper half, it's a violation.
Yeah, see, you have to imagine that there is a diagonal, right? See, I'm telling you an easy way to visualize violation, which you have to patiently first listen to. Okay, see, this is what I'm calling it as violation. You geometrically, then we will see what it means. Okay, suppose you have n Rs and n Us. Okay, now my violation is one in which at any point, if number of U's is greater than the total number, if total number of U's is greater than total number of R's, then it's a violation. So that's what I'm saying. Suppose you had 2 rights and 2 U's. Let me write down all the 4 cases. 2 example, 2 U's and 2 R's. Okay, so then you are going to have UU, RR. This is a violation. RR, UU. This is not. Let me put violation. I'm going to say tick mark. This means violation. Not a violation means not a violation. I'm going to say. Okay, so like this, how many ways are there in which we can do it? Let's try to exhaust it. So this is 1. This is 2. Can you help me with the other ways? RU. This is 3. This is not a violation. UR. This is a violation. Sorry. See, I hope you get the idea. How many violations are? These are not violations. I've given some examples of violations and some more. So another example. Is there any other possibility of violation?
RU.
No. Only 2 U's and 2 R's are there. One by one. Can you tell first person?
RUR.
Okay, so I have not written it. This is a violation. Correct. Very good. Yes.
URRU.
URRU. Is that correct? Yeah, we have not written it again. Okay. Anything else? So non-violation also you can tell me. So we'll see for 2, how many possibles are there? 4 factorial by 2 factorial into 2 factorial ways you can arrange, which is going to be how much? 6. I think there are no more ways, right?
Yes, sir.
Okay. So then this is done. Now you count 1, 2, 3, 4. These are the violation cases. Now for n is equal to, this is corresponding to Catalan number what? So for which Catalan number you get 4? Is there any Catalan number which does 4? I think there is some small trouble here, right? Even equal, is it considered violation? I'm just trying to think. Is that what you're trying to say? So are we considering it as a violation or not? That's the question.
Sir, which one you are telling?
No, sir, that will just touch the diagonal and leave.
So
it will just It
No,
will
even
just touch the diagonal. It won't cross the diagonal.
no, it won't cross the diagonal. So, but see, ultimately, the okay, I think this is fine. This is correct, right? Yeah. So basically, this corresponds to, yeah, I think this is fine. So this is okay. So strictly greater is what we are going to call it as violation. So this corresponds to Catalan number 2, right? All right. Is it
Yes,
C1? Is it C1 or C2? Is it C1 or C2? What is C1? C1 is, okay. C1 is 1 by 2, 2 into 1, 2n, choose n. N is 1 here. So this is going to be C1. C2 is 1 by n plus 1, which is 3, 2n, n is equal to 2. So it is 4 choose 2. So 4 choose 2 is 6 by 3, it is 2. So this corresponds to C2, right? So if you geometrically look at this, RRUU and RURU, then it corresponds to RURU. This is one configuration, which is fine. RRUU. So these are not corresponding to violations. But you look at the first one, UURR, it is a violation because immediately you are crossing the diagonal. So you have to consider that. I hope it is clear to you now. Is this fine? So in this example also, this doesn't correspond to violation and this corresponds to violation, UR, because we have crossed the diagonal instantly. So take the corner case into account. I hope it is clear.
yes, sir, it's clear.
Yeah. Still, anyone has a question there? Okay. Yeah. Okay. I think we are already running out of time. It's beyond 5. So maybe we'll stop here. So there are a few more questions. I think the TS should be able to help you guys with that. Okay. Maybe we can discuss that at a later point, or maybe during the next live session if you have still questions on that. But I think you should be able to work it out. How many ways 3 persons having 6 1 rupee coins, 7? Okay. Donate 10 1 rupee coins collectively. So I think it comes in the total sum as 10. So x1 plus x2 plus x3 is equal to 10. Okay. So he can give from 0 to 6. The second guy can give from 0 to 7. And third guy can give from 0 to 8. So total sum x1 plus x2 plus x3 equal to 10. And then you have this constraint x1 less than. So maybe I'll write it down maybe quickly because we are already running out of time. I'm assuming this is what the question is talking about. You can possibly see there's already a discussion on this, how to compute this. And what is the second guy can offer 8. So how many ways can 10 rupees can be generated? So using generating functions, you can do it, or using possibly, I think using generating function, it becomes easier, right? 1 plus x squared till x power 6. You try to find the number of coefficients, 1 plus y square and so on till y power 7, 1 plus z plus, or basically you have to compute what is the power of you will have to verify. I am not verifying. I'm just, so you need to compute the coefficient of x power 10 in this product, right? So that is the possible number of solutions, right? Yeah, if possibly you can simplify it in some cases. In this case, I'm not sure whether we can. Yeah, I think we can simplify. So you can make it as an infinite sum also, right? Maybe but yeah. So you can simplify it and try to do it as well. In this case, you think about it. Okay. All right. So maybe we'll stop here. TS, are you guys there?
Yes, sir.
Okay. So other questions maybe possibly can be taken in TS session. But if there are any last questions, I will possibly take it. If not, we'll end this live session for today.
Okay, regarding the rest of the question, you can post in the discussion form. You can reply
Right.
there and we can discuss there as well, right? And the solutions for the assignment will be shared soon.
Okay. Good. Okay. Thank you, guys. Thanks for participating. Yeah. All the best. Bye.
Thank you, sir.
Yeah, thank you, guys. Rest of you guys.
Thank you, sir.
Thank you, sir.
Thank you.
Oh, yes, thank you, sir.